So let's go back. Well, next thing we're going to do, we're going to move on to another example, a similar type of problem, but with the idea of illustrating some alternate approaches to modeling resistance in these some things that we wouldn't necessarily recommend, but there are other approaches that are taken. Okay, so in this problem we have what do we have? We have a conducting material here. This is our conducting material. It's adiabatic, so there's no heat transfer out in the vertical direction. And we're held over on this side at TH equals 300 and on this side at 100. So we have heat transfer right this way. And we're given this other geometry. We assume there's some width, centimeter into the page, but it's basically symmetric, right? So there's no heat flow in and out of the page. Okay. So what we want to do here is look at how we could model the resistance. So let's start with, first of all, looking at what we've already done, right? The isothermal and the adiabatic. So let's start by building an isothermal model. So if we're to compute the total resistance between TH and TC, we have two conduction resistances, right? Those two conduction resistances would be in series. So we can say our isothermal model, our ISO, would be the sum of those two things in series, which would be, let's see, L1, which our thickness is L1. This is a plane wall, L1 over K, and then the area, H1 times W, plus L2 over K, H2 times W. Right, so this, we're kind of assuming that the heat can magically expand as it goes through this little restriction and has the full area available to it. All right, the other approach would be adiabatic limit, and then, oops, there we go, adiabatic limit. As you can guess, this would be our adiabatic is now L1 over K, H1 times W plus L2 over K, H1 times W, right? We're assuming that the heat can only continue to flow within that restricted channel. Okay, so we go through, now let's say we calculate the heat transfer based on this, right? Q dot up here is equal to T H minus TC over R. If we plug in whichever R we have here, let's just compute the Q dot. So Q dot is, so Q dot is, for this model, 6.67 watts. For the adiabatic model, right, stop and think. So is adiabatic going to be higher heat transfer or lower heat transfer? Guesses? Lower, right? Because the resistance is going to be higher. So this turns out to be 3.33 watts. Okay, as I said, okay, so this is our balance, right? These are the physical limits on what could occur. So let's look at a couple other models that are commonly used and do a little bit of analysis on this. So there's one called the average area. So the average area model. And the idea there is you're going to compute some R based on a bar, right? On an average area that's available for heat transfer. Okay, so we would say our A bar for a plane wall is the length over K times A bar. Same idea for resistance. But A bar is computed as the length integral, so the 1 over the total length times the integral from 0 to L of A as a function of X dx, right? Assuming what? So this direction here is X. This is just the length average integral. All you're basically doing is you're taking the area of each segment, the length according to them, and doing a weighted average. Right. For this model, if we did this computation, we would say Q dot is actually equal to 10 watts. Okay. Where did we get 10? How did we get to 10 watts? So we just decided 6.67 and 3.33 are the limits on this problem. Physically, those are the actual limits. So how did the area model get us to 10 watts? Right? It is really confusing, but this goes to illustrate why this particular model kind of sucks. All right. The idea is that let's do a little bit of a thought experiment, and this might help us understand a little. So let's see. Let's say that let's take the limit. So if we take the limit as what? H1. H1 goes to 0. So let's imagine that here H1 is this guy here. So let's say this, we further constrict this to the point where it's 0. Then we compute the resistance for each of these different models. Right? What's the actual resistance? Right? The actual resistance if H1 goes to 0. Yes. Right? The actual resistance is infinity. There's no way for heat to get through there. There's nothing to conduct. Right? There's no area available for it. So there's nowhere for heat to go. Okay, for the isothermal model, what would it do? Well, isothermal is saying that's again L1 over K H1 W plus L2 for K H2 W. What happens to that? Okay, this goes to 0, right? Yes, infinity. Infinity plus something, which is infinity. Okay, so that's okay. R adiabatic, L1 over K A1 W plus L2 over K A1 W. Yeah, double infinity, which is infinity. Okay, and then now we have our area model. So in our area model, A bar is going to be what? It's going to be 1 over L times H1 times W times L1 plus H2 times W times L2. All right, so we said what? H1 is going to 0. So this goes to 0. Area does not go to 0. Average area does not go to 0 though. Right? So you still have an area available for conduction. So our A bar does not go to infinity, right? It's a finite answer, which it physically is impossible. So the average area model is actually, in some cases, okay. In some circumstances, it's okay. But if you have a very big difference between the biggest area and the smallest area, it is not a good model. Okay. So let's see. So then the last thing was the average length model. This is another option. Average length model. And the idea here is, let's say we have some surface, and that surface is kind of like oops, great. So that's the average, okay. Like this, and it's like this. All right, and here's our kind of average position for each side. The average length model attempts to compute the total resistance based on the distance that the heat has to travel in this direction, right? The average distance. So the kind of formal way of writing this would be, okay, our L bar is equal to L bar over KAC, where this area here is AC, the cross-sectional area. Right, and then L bar itself is computed using the area integral of length. So 1 over area, integrate over the area of L dA. Okay, and this actually is bad, but in the opposite way of the other one. And again, if you think of our thought experiment, let's imagine I'll just draw it a different color. So let's imagine there's a point in this model where it actually, the two surfaces touch, right here. What's the resistance of this thing on the whole? 0, right? Heat will just flow through that the path of least resistance. It's just going to go right through that 0 point of resistance. So the fact that you've got this average length, that's great, but it doesn't give you a good indication of what the actual heat transfer is going to be, right? So there are limited circumstances where this is okay. Again, maybe if they're all about the same order of magnitude, the lengths, it's okay, but it's important to understand what you're actually doing when you use these different models. models and how they relate. So let's kind of put everything in a hierarchy, all right? So we're going to say our actual R is here. And we're going to kind of sort out what the resistances are for the four other models we talked about. All right, so the actual resistance is going to be between the isothermal and the adiabatic. Right, adiabatic is always higher than the actual resistance, and isothermal is always lower. Okay, and it turns out that the average length model, remember we got, let me do this one first. So the average area model is down here. Right? The average area model told us 10 watts when in fact the bounds should be between 3 and 6. So that implies that the average area model's resistance is actually much lower than even the isothermal. And then the average length is bad in the opposite way. So here we have our L bar over here. So anytime you're using these models, you're going to have this kind of hierarchy if you're using the different assumptions. Area average is always less than isothermal, which is less than the real, which is less than adiabatic, and the average length. Okay. Any questions on this so far? No? Good. Okay. All right. So let's see. Actually, that's all I had for today, but I think what we'll talk about next time. So far, we've only dealt with conduction, 1D conduction, steady state, no generation. Next time, what we're going to be doing is talking through the possibility where generation is occurring. So generation is a phenomenon where you have energy changing from, say, electrical or chemical or whatever into heat within the domain on a volumetric sense. Like it sort of spread throughout the volume, it's changing to heat. And then we have to modify how we go through the energy balance and solve the ODEs to handle that. Okay, thanks everyone.